Yes, sir.
Yeah. So I will quickly go on to give me a second. Yeah. Where were we? So if the Reynolds number is between 0 to 2000, then the flow is laminar. If it is above 3000, then the flow is turbulent. And if it is between 2000 and 3, yeah. So then it is, of course, 2000 and 3000, it is unstable. Now, in this question, which we are actually seeing, you will see how many things are already mentioned. The flow rate of water at a tap of diameter. So the diameter of the tap is given and flow rate is given. Do you remember what was flow rate in the last class? Basically, the value of Q. Okay. So the value of Q, which is actually the amount of volume of water in a given amount of time, Poiseuille's formula, that is what we call as the rate of flow as well. So more the liquid, as you can see, there are two rate of flows, 0.48. So less amount of liquid is flowing in a given amount of time. 3 liters per minute, more amount of liquid is flowing in a given amount of time. Okay. Now, I will quickly tell you how to go through these types of problems. So first of all, the value of diameter, coefficient of viscosity, and of course, we know the density of water. These three things are already mentioned. But as we know that the value of volume of water flowing out per second is equals to volume into area. Do you remember how are we making this particular formula? Do you remember it?
So Poiseuille's formula.
Yeah. So from Poiseuille's formula, how do we come up to this particular point? Basically, the value of Q is equals to V by T. Am I right? Volume by time. This is V is volume. Now, volume can be written as area into length by time. And the value of length by time is actually equals to what? Velocity. So from there, actually, we get the value of Q is also equals to velocity into area. This is also a very important thing because now area can be written as pi d square by 4. You very well know that, how to calculate area and all. Now this velocity formula, which is of course not a formula, but we made this formula, we will use this formula in a very efficient way. How? The Reynolds number thing. So this was the basic formula for Reynolds number. This is the original formula. But in this one, how many things we already know? The diameter is already given in the question. Then density we know and coefficient is also given in the question. Only the term velocity is unknown to me. But we now know that I can easily calculate the velocity by this particular formula. Am I right? So I can calculate velocity by this, and I can pick the value from here and I will put it in this particular thing. Yeah. So as I will put it, you will see that there is a new formula, kind of a new formula for the Reynolds number. I will not say that, oh, please remember this formula or something. No, but this is kind of an important one for this question. Why? Because if you will see, all the things are known to me now. That is density. Then there is rate of flow. Then there is diameter and the coefficient of viscosity. All the things are known to me. I can easily put the value. Okay. So if I am talking about 0.48 liters per minute, the rest of the things are also known to me. So when I'm talking about 0.48 liters per minute, you will see that the Reynolds number is coming out to be 815. You can do the calculations later, okay? But when Reynolds number is equals to 815, can you tell me what type of flow is this? Exactly, because this number is actually less than 2000 actually. It's even less than 1000, but because it is less than 2000, without a doubt, this will be a laminar flow. Okay. Yeah, you can also call this a streamline flow as well. Now, similarly, when the question is also mentioning another type of flow, that is 3 liters per minute. So if you take 3 liters per minute, everything else remains same. Density remains same, diameter remains same, then coefficient of viscosity remains same. Everything is same. Only the flow rate changes. That is 3 liters per minute. Now, what can we do in this situation? We will again solve and you will see that the number is coming out to be 5096. Now, this Reynolds number is actually what? This is clearly more than 3000. So what type of flow will you expect by this? What type of flow is this?
Turbulent.
Exactly. This is a turbulent flow. Okay. This is very, very important actually. How to understand the turbulent flow or laminar flow? This is all basically you can use the concept of Reynolds number. That's the best way out. Okay. Fine. Next. Okay. So next is the equation of continuity. But before understanding it, imagine you have a pipe like this. So can you tell me why do we actually put our thumb on the pipe like this? What's the main reason of doing it?
To reduce, like either to reduce the amount of water coming out or like the speed of the
We want
water.
the water to go with a higher speed. Am I right?
Yes,
That's
sir.
the main purpose. This is what we will actually talk about now. That if I put the thumb, and before putting the thumb, there were two scenarios. So when actually I was not putting the thumb, area was actually more and velocity was comparatively less. But as soon as I'm putting my thumb, I'm reducing the amount of area and automatically velocity increases. By this data, this is not even a data. I can say this is just a simple experience you all have gone through. Okay. So area is increasing, velocity is decreasing, area is decreasing, velocity is increasing. Clearly, area is inversely proportional to velocity. Okay. Yep. So, or I can also say that the product of area and velocity is actually what? Constant. So if I say something like this, velocity will go here and it will be a constant. So can I say that A1 V1 is equals to A2 V2? Yep. That is the product
Yes.
area and velocity is actually a constant. So this was coming out of from a basic data, but actually there is a small derivation out of it. Although we are not discussing derivation today, but I can simply tell you this thing which I am telling you, that is the product of area and velocity is constant. This is known as equation of continuity, which is very obvious, very obvious. So if the pipe is having a bigger diameter, the water will come out slow. But if you will actually make the pipe very thin, then the water will come out at a higher speed without a doubt. Okay. So we can say product of area and velocity is a constant, or we can say area into velocity, A1 V1 is equals to A2 V2. Yep. Very simple. This is known as equation of continuity. For example, I will show you one problem. So as you can see this one, the question says water flows through a horizontal pipe with the internal diameter is 2 centimeter at the speed of 1 meters per second. Okay. So there is a pipe. Yep. Having a diameter of 2 centimeter and the velocity of the water is 1 meters per second. What should be the diameter of the nozzle if the water is to be emerged at 4 meters per second? Now, what do you want? You want to change the area. Okay, somehow you want to change the area. I don't know the diameter, of course, but you want the velocity of the water coming out to be slightly higher, which is 4 meters per second. Now, if you want to increase velocity, what should you compromise, Elizabeth? What should you compromise?
Making the area smaller.
Exactly. We need to make the area smaller. Okay. So we have to decrease the area, decrease it, and your work will be done. So what we will do in such a situation is quite simple. That is, take the diameter and you can easily calculate the area. Of course, the formula for area is pi d square by 4. So what are the things which are there with you? First of all, diameter is there, velocity is there for situation 1. Then velocity for situation 2 is there, but the diameter is not given. That is what you have to calculate. So what can we do? Just put A1 V1 equals to A2 V2. This is the equation of continuity. All the three things are given to you. That is, the value of A1, V1 and V2 are given. A2 is actually what? Unknown to you. Calculate it. It will be easy. Is that fine, Elizabeth? Yeah.
Yes, sir.
Who else is there? Yeah. Now, next is also very important, or you can say the most important part of this chapter. That is known as the Bernoullis Principle. So, before talking about Bernoullis Principle, I want to tell you few things which you should understand. Okay. So, you very well know about the concept of kinetic energy. That kinetic energy is equals to half mv square. That is clearly not new for you. That's not new. But if you actually take kinetic energy, which is equals to half mv square, and you divide it by mass, so mass and mass will get cancelled out, it will be equals to half v square. This is known as kinetic energy per unit mass of the liquid. Is that clear? Yes.
Yes, sir.
And making it more different, so if I take the kinetic energy half mv square, and if I divide it by the weight of the body, that is mg, so if I divide it, m and m will get cancelled out. Answer will be v square by 2g. So when I divide kinetic energy by the weight of the particular liquid, this is what we call as the term kinetic head. Oh, where is it? Velocity head, or kinetic head as well. So velocity head is the term used for it. So dividing kinetic energy by the weight of the body. Okay, very simple, very basic. Similarly, imagine what is the formula for, can you tell me what is the formula for potential energy?
mgh.
Mgh divided by mg, what will you get?
H.
H only. That is what we call as the potential head. Okay. Potential head is only H because you are taking mgh and dividing it by mg. That's it. That's it. Okay. So, and you can also say that potential energy per unit volume means taking potential energy, dividing it by volume, you will get rho gh, because mass by volume is equals to rho gh. Why am I talking about these things? Because these things will help you a lot while making the equation. That is known as Bernoullis Principle. So now imagine there is a situation that there is a pipe with one area to be bigger, one area to be smaller. Basically, you can say there is a change in area. One is having a different height, another is having a different height. Now, if you have kind of a pressure in that situation, of course, the velocity is going to change as well. Because of the area as well, the velocity will change. So there are three things involved in this whole situation. First of all, velocity, which means the kinetic energy of the body. Second, height, that means the potential energy of the body. And third is the pressure. Okay. So from there only comes the Bernoullis principle. That is, if you take all the three of them, that is, if you take the, first of all, kinetic energy, potential energy, and pressure energy. Pressure energy is kind of a new term for you, but not a big deal. All of them per unit volume. Per unit volume means, just like I am saying, half mv square, dividing it by volume, mass by volume is density, so half rho v square. Okay. Similarly, mgh, dividing it by volume, mass by volume is rho gh. My point is that if you take kinetic energy per unit volume, potential energy per unit volume, pressure energy per unit volume, if you take all the three of them, basically the sum of all three of them, that is actually equals to a constant. Are you understanding my point, Elizabeth? This is Bernoullis principle. There is a proof for it, although we are not discussing the proof, but are you understanding my point?
Sir, could you show the, sir, V is equal to rho G? No.
V is equals to rho G. Can you repeat?
Sir, like P divided by rho G. Sir, could you show how that is?
I will talk. Okay, I have not talked about this yet, but okay. Pressure energy, if you are asking, it's not a big deal actually. So if I'm talking about pressure energy, it's all about the energy possessed by a liquid by the virtue of its pressure. That is, of course, pressure energy. So the pressure is causing some sort of energy. That's it. Okay. Now if I'm talking about the formula, I will not go in extreme detail, but I think you know that work done is actually equals to the product of pressure and volume. Can I also say that for now? Pressure and volume. Yep.
Yes, sir.
Okay, let's see. It's like this, that work done is equals to force into distance. Force is equals to pressure into area, And now area into distance is actually equals to what? Volume. So this work done is coming out to be PV. And as we know that work done is equals to energy, which is equals to PV. This is what we call as pressure energy. Now pressure energy is PV divided by volume. That will be left with P only. That is pressure energy per unit volume. Is that fine, Elizabeth? Is that okay?
Yes, sir.
That's it. So this is what we call as pressure. Yeah, here it is. Pressure energy per unit volume, PV by V, which is equals to P. We can also call this excess pressure. Of course, if you don't have pressure in the pipes, they will of course not go up to a higher height. Imagine it in this way. Water is going above in a pipe. That will not happen without pressure. You cannot do it. Okay. Now, if I'm talking about PV, and if I divide it by mg, of course, you are dividing pressure energy by the weight of the liquid. What will that be called? That will be known as pressure head, just like kinetic head and potential head. Are you understanding my point? Yep.
Yes, sir.
So what will happen? Finally, it will be what? P by rho g. So P by rho g is actually the pressure head. Now coming back to the point, just like we say that there is what we call potential energy per unit volume, kinetic energy per unit volume, there is pressure energy per unit volume. The sum of all the three of them is what we call as it is equals to constant, which is Bernoullis principle. Or we can say the sum of pressure head, kinetic head, and potential head is also constant. This is also Bernoullis principle. Is that fine to you? Yep.
Yes, sir.
Okay. So this is Bernoullis principle, very useful, very like this will be used in a lot of different areas. Actually, you will see how. I will show you how. Now, I will, of course, I'm not explaining you derivations, but that doesn't mean I will not explain you the basic theory behind it. Imagine there is a container. So if there is a container like this, which is actually closed, yep, and you have made a small hole in it so that the water goes out and from there, yeah, like you have a particular container, you are making a hole in it, so of course the water will fall down. So what are the three things involved? Pressure here, pressure here. That's the first thing. Second thing is that liquid will come, like go out from here, and the liquid over here will also fall down. That is the kinetic energy. And the third thing is, of course, the potential energy. So this liquid is at a certain height, and this liquid is at a certain height. So that is the potential energy. Are you understanding my point? The three things: pressure energy, kinetic energy, and potential energy. Are you understanding it?
Yes, sir.
Now, of course, you will do again the same thing, that you are equating all the three things. You are saying that, oh, it is constant. So you will be doing P1. Basically, you will write an equation like this, That is P1 plus half rho V1 square plus rho G H1 is equals to what? P2 plus half rho V2 square plus rho G H2. So when you will write it, you will finally get a formula for the velocity. What is this velocity? This is the velocity of the liquid which is coming out of this particular hole. Yeah. Imagine I have made a hole in my water bottle, and now I want to know the velocity with which the water is actually coming out. So if I want to know the velocity with which the water is coming out, the formula is this. Ignore everything else, ignore it, but understand only the formula for now, which is equals to root 2gh into like 2p minus pa by rho. Understand this formula as well. Of course, you can just like not cram it. H is actually the height of that hole from the top of the container. That is H. Then P is actually the pressure inside the container. That is P. And PA is the atmospheric pressure, because this hole is in contact with atmosphere. So that is atmospheric pressure. Understanding my point? Is that okay, Elizabeth?
Yes, sir. Yes, sir.
So now I will use this particular formula in multiple situations. How? Imagine a situation where P is very greater than PA. Can you think of an example? This one. Although I may be exaggerating it, but this is one of a good example. As you know, that the pressure inside the like soda and bottles and whatever, so the pressure over here is kind of very big as compared to the atmospheric pressure. Okay. Yep. Let's suggest it. Of course, there is not that big of a difference, but still, let's consider for an example. And this is a closed container as well. Now, if P, that is the pressure inside the container, is very big as compared to atmospheric pressure, and now you are making a hole in that particular bottle. So with what velocity the liquid will come out? So the liquid will come out with a velocity this. Why? Why? Because as you can see, the original formula is this, that is 2P minus PA by rho. Now, because P is very bigger than PA, this term is actually big. Okay. Automatically, this term in the formula becomes big. And it becomes so big that this term over here can be neglected. I can neglect it. Or I will say ignored. So let's ignore this particular term because it's so small. And that's why you actually come up with a formula like this. Okay. But again, this is just a special case, special condition where the container is actually filled with a lot of pressure. This was just an example. I am exaggerating it. The actual example can be like a rocket thing and all. Yeah, here it is. Such a situation exists in the rocket propulsion. Okay. So not in a bottle or something, but for understanding, I'm saying it. Are you getting it, Elizabeth? Can I move ahead?
Yes, sir.
Okay. Now, again, another situation. What if I am talking about a situation where I have a container which is open to atmosphere? Open to atmosphere means that I am making a hole, velocity is there, but this part of the liquid is also in contact with atmosphere. So it will be having atmospheric pressure, and also already there is atmospheric pressure over here. So when you will use the formula, so this P minus PA will actually become PA minus PA, atmospheric pressure minus atmospheric pressure. So the whole term will actually become what? Zero. So we will be only left with this. And this is what we call as what? Root 2GH. And this is also known as the Torricelli's law of efflux. Why? I will explain. But tell me, are you understanding the formula first of all? Are you understanding it?
Yes, sir.
Can you tell me what is the formula for the velocity of a body falling from a height h? Imagine a body is falling from a height h. So what will be the velocity here? If I am dropping it, initial velocity is of course 0. What will be the formula?
Sir, also root 2GH.
Root 2GH. Yeah, of course, we will apply V square minus U square is equals to 2GH. This is 0, so V square is equals to 2GH. And finally, we'll see V is equals to root 2GH. So the same formula is there for a falling body, and the same formula is there for a liquid coming out of a small hole. Yeah. So that is why we call the velocity of efflux of a liquid is equal to the velocity with which the body is falling freely from a free liquid surface. Basically, that's the whole thing. Okay. Now, this was Torricelli's law of efflux. Next is Venturi meter. Now, before explaining this, I want to go again to this particular concept. Yeah. And I'm rewriting it. Let's rewrite it. That is P1, or let's write just P. P plus half rho V square plus rho GH is actually equals to a constant. Now, why am I doing rewriting this equation? Imagine I don't have a pipe like this. I have a pipe like this, a horizontal pipe. Horizontal pipe means that if this is the ground level, this end is also at a height of h, and this end is also at a height of h. So can I say that if I write this equation in this form, that is P1 plus half rho V1 square plus rho g H1 is equals to P2 plus half rho V2 square plus rho g H2. So this term and this term, they will be equal to one another. And I have to ignore these two terms. So they will be cancelling out because the pipe is horizontal. Yes, Elizabeth?
Yes, sir.
Okay. Now, by ignoring this term, let's move ahead. So the remaining two things, that is P and V, that is pressure energy and kinetic energy, will be a constant. Now, if this is a constant and one thing increases, the second needs to decrease. It's a very simple thing. It's like if you have the sum of x plus y equals to 10. Okay. And if I say that, oh, x is equals to 5 and y is equals to 5, they are equal to 10. But if I want to increase the value of x, then I have to certainly decrease the value of y to get the same answer. That means if I increase pressure, I have to decrease velocity, or if I increase velocity, I have to decrease pressure. Am I right? Yep.
Yes, sir.
So I can say that pressure and velocity are actually inversely proportional. From this data, I just want to say that pressure and velocity are inversely proportional. Basically, the areas or the region where the pressure will be high, velocity will be low. And the region where pressure is low, velocity will be high. Are you getting my point? Yep.
Yes, sir.
Why am I saying it? Because I will use the same situation for a lot of different areas. A lot of different areas. That is, let's imagine a situation for an atomizer or a spray, whatever basically you can call it. So how it simply works, there is a pipe connected to the liquid. You actually press it. So when you press it, what happens? You are throwing out all the air. So when you are throwing out all the air, something needs to fill this gap. And now if something needs to fill this gap, air cannot come inside because the air is already going outside. So air cannot come inside. So who will fill this particular gap? Who's going to fill it?
The liquid, the fluid.
Exactly. The fluid from here will go up and it will start filling the gap. And because you are throwing out all the air, what happens? The pressure in that particular pipe decreases. And automatically velocity increases, and that's why you see something like this to be happening. A very simple process, but again explained through the Bernoullis principle. Understanding it?
Yes, sir.
Similarly, dynamic lift, which happens in the airplanes and all, Magnus effect as well, a lot of people call it. What happens? The wings of a airplane is made in such a way that it helps the plane to actually go in the upwards direction. How? So it is made in such a way that the upper streamline or the air which is going from upper part of it has a higher velocity, and the lower part of it, lower streamline, has a lower velocity. Now, can I say that this is happening due to the shape? Yep. And the other thing, that is, because of low velocity, you have a high pressure, and because of high velocity, you have a low pressure. This happens due to Bernoullis principle, basically inverse relationship. Yeah. So you have a high pressure situation below, you have a low pressure situation above. Due to that, what happens? There is a help, or you can say a push in the upwards direction. Because the air is pushing it in the upwards direction, this is what we call as dynamic lift. Okay. Understanding it, Elizabeth?
Yes, sir.
Same goes on with another situations as well. When you are kicking a football, same goes on. You don't have to go in extreme detail, but you can say that when it takes a turn like this, it is doing the same thing. That in one side of that particular football, flow rate is fast, pressure becomes low. And on the other side, flow rate is slow and the pressure becomes large. And that's why you see a shift or dynamic shift in a particular football. Same goes on when we are talking about the tornado and the rooftops of the houses are blown away. Same thing happens because the wind is flowing so fast that the velocity on the outside is high. Okay, velocity is very high, and of course we can imagine that velocity inside a house will be of course low. So what happens that pressure inside the house becomes bigger as compared to pressure outside. Low velocity, high pressure, high velocity, low pressure. And that's why it pushes the rooftop in the upwards direction and it gets blown away. Getting my point? Yep.
Yes.
So this is the same thing happening in all the situations. Okay. So everything which we have learned until now, basically the Venturi meter as well, it also works in the same way. Exactly. Yeah. I will just tell you the rate of flow or Q. I have used this right now, so you know it. The rate of flow, basically the volume of the liquid flowing out per second, can be represented by this formula. Okay. Where what are the things involved over here? First of all, area of this section A1, area of the smaller section A2. And of course, this one will have a smaller velocity and this one will have a bigger velocity, V1 and V2. Fine. Then in this case, how are you creating the difference in pressure? So you are creating the difference in pressure using the liquid. As you can see, there will be a difference in height. So because of this difference in height, we know that there will be a pressure which is known as H rho G. Do you know this formula? Pressure?
Yes, sir.
So this difference creates a pressure difference, and that is what the main reason of the flow of the liquid. Overall, this is the formula. Slightly complicated. I agree. The formula is complicated, but the theory is not. You will do 2-3 problems and it will be done. All the questions out of Bernoullis principle are doable if you know the concept. That is, when pressure will increase, when velocity will decrease. If you know it, questions are solvable. Okay. So I've added a lot of good questions over here. Try doing them. This one, very important, a very good question. Try doing it. This one also, try doing it. All of the questions which I have mentioned over here, all of them are doable. Good questions will give you a lot of practice. So you can do them. And every particular formula we just learned. So formulas, I can agree that this particular formula for the Venturi meter is slightly heavy. But other than that, that is Torricelli's law of efflux, then equation of continuity, then Bernoullis theorem. Bernoullis theorem is easy to remember because it is actually of 3 different parts coming together. So that's why it becomes easier. So only one thing is slightly complicated. That is the Venturi meter. You can do it by doing 2-3 problems and it will be automatically inside your brain. Okay. Now, next is how much time do we have left? Give me a second. Okay, so we still have 5 minutes, so I will quickly cover a few topics. First of all, cohesive force, and second is adhesive forces. So you might have seen adhesive written at a lot of places like Fevicol bottles and all of that. So adhesive force means the force between 2 different bodies. Yeah, imagine a water molecule in contact with the glass surface. So the force between them is adhesive force, whereas the force of attraction between 2 water molecules is what we call as cohesive force. I think that was pretty simple. Why is this important? Because this causes actually a difference in the meniscus. What is meniscus? I will tell you. Basically, when you will put mercury in a test tube, have you ever tried it? When you put it in a test tube, it has a curvature like this. It is having a, yeah.
Sir, Not for mercury, but for
So,
water. you did.
yeah, you might have seen this thing. Yeah,
Yes,
you
sir.
can see it right now. You can open your refill in your pen and you will see, because it's a very thin tube, so you will see there is a meniscus over here. And because of this meniscus, like this curve over here is known as meniscus. This is actually the reason of the whole cohesive force and adhesive force. How? See, basically, if you have a situation like this, where the meniscus is like this one, so what's the main reason? Because the force between water and water is weak, and the force between water and the glass is comparatively strong. Similarly, why is there a curve like this? Because the force between mercury and mercury is strong, and the force between mercury and glass is comparatively weak. Hmm? So what can I say? That if, I will repeat everything, if the adhesive force and cohesive force are basically equal to one another, then there will be no curve or anything. The liquid will be straight. But if you have the adhesive forces weaker than the cohesive forces, which happens in mercury, so the molecules of mercury are actually having a very strong force with one another. So their cohesive force is strong, adhesive is comparatively weak. So that's why mercury is not even wetting that particular container in which you are putting it. You will see a curve like this. This is known as convex meniscus. And opposite goes on with water. That is, when adhesive is more than cohesive, you will see a curve like this. Are you understanding my point? Yep.
Yes,
Elizabeth?
sir.
And the angle which is actually over here, this angle is known as angle of contact. Not added it over here. No worries. Basically, what can you say? That if you have a liquid curve, so if the liquid is having a curve like this, so this curve, if you make a tangent like this, if you make a tangent, so this tangent is making, of course, some sort of angle with the container. So this angle is known as angle of contact. Same goes on if you have another type of. So if you have a convex meniscus, again, this angle is what we call as angle of contact. Okay, clear? Yep.
Yes.
Yeah. Oh, I'm really sorry, not this. Sorry, like this. Yeah. So this particular angle is clearly acute. So acute in the case of water because cohesive forces are weak. And in this particular case, it is obtuse in the case of what? Obtuse in the case of mercury because cohesive forces are strong. Okay, fine.
Yes, sir.
Okay, that's it for today. I thought this chapter would be completed by today, but it's not, so no worries. We will take one more class and we'll finish it off in the next class. Fine. So it will not take me more than 15-20 minutes. So this chapter is remaining, a very small part of it is there now. So we'll discuss it. All the questions which I have mentioned, try it out. If you have a doubt, come up with that. We'll discuss first doubts, then the remaining topics, then we will switch to the next chapter. Okay, fine.
Okay, sir. Thank
Okay,
you.
bye bye. Thank you so much. Bye, both of you. Bye.